So thank you, organizer, and thank you, gentlemen. I'm very pleased to be here to present our work on bipedal robot. The title of the presentation is 3D Simulation of Human-like Walking and Stability Analysis for Bipedal Robot with Distributed Sole Force Sensors. The authors of the papers are Mr. Xi Qiu and myself, and I'm the presenter of this paper. We're both with the Department of Mechanical Engineering of the Hong Kong Polytechnic University. The objective of the work is to study the human-like walking of bipedal robot and analyze its stability with distributed force sensor model. As you know, the bipedal robot has an advantage over the wheel ones because they're more flexible. They can walk over uneven terrains, right? Unlike as compared to the wheel ones. And now our work actually referred to a number of literature. The first one, published by Lee, he achieved a human-like walking with straightened knees, considering toe off and heel strike and different gait lengths. Ogura achieved human-like walking with knee stretch, heel contact, and toe off motion with robot, which has a passive degree of freedom in each foot. EZMP, the zero movement point by Bratovic and Borowick, is used in bipedal robot stability analysis and control regardless of different walking patterns. Larry manipulates the EZMP of a bipedal robot considering the walking with foot rotation. And lastly, Nikolic assumed the point contact as a 2D spring damper model and the foot-ground interaction as a matrix of single point contact. This is the model of the bipedal developed in our laboratory. And the features of this bipedal robot are the 10-degree freedom. The mass property can be derived from SolidWorks and is human-like with similar thigh-shank length ratio. Now we use the steam mechanics model for the bipedal robot, and the features are they got the same mass and dimensional property as a physical robot. The kinematic variables for each body part can be obtained, and it's easy to analyze its stability during walking. Now, as for the model, we have two. The first one is a ground contact model, and we use the spring damper model for the lumbar force and the Lagrange model for the frictional force. And this graph shows the response of the force at the 4 points of the foot sole. And for the lumbar force, when the deformation is less than 0, we have 0 actually. And when the deformation is greater than 0, you have a damping effect and the spring effect. And then for the friction, we consider two types of friction. The static friction, which is equal to mu s n. Mu s is the coefficient of static friction. And for the kinetic, we use Fc equal mu Cn. And we also use strike back curve for the stiction, right? And here, the SV is the function. And S is equal to this expression, Fc plus Fs minus Fc, exponential e to minus V over Vs to the power delta Vs. Delta Vs is the shape factor, and Vs is the strike back velocity, and V is the relative velocity between two contacting surfaces. If V is less than Vs, the contact can be regarded as a sticking contact. So at the macroscopic level, the average deflection of two surfaces, Ez, can be modeled by this first-order differential equation. And sigma O is the aggregate Bristol stiffness. finally, we get the friction from this expression, F equal to sigma O Z plus sigma 1 Z dot plus sigma 2 V. And sigma 1 and sigma 2 are the damping coefficients for the stiction friction and the kinetic friction, respectively. So we also use a distributed force tensor model for the foot sole. And here you can see I consider two parts. The first one is the heel part, and the second one is the frontal part. And you can see altogether the number of sensors placed on the foot sole. And we use a separate core system for each sensor, right? And then we talk about the simulation method. Now, first, we need to develop the foot trajectory. Now, for human-like walking, there are three different walking phases. The first one is the heel lifting phase, the swing phase, the second one is the swing phase, and the last one is the toe striking phase. So we all define all these parameters, and this as initial is the initial position, L foot is the length of foot, and also we define the step length as T step. And there are two angles. One is the lift angle, and the other is the heel angle, right? So this heel angle, and this is another angle, right? Strike should be the strike angle. And now, for the heel lifting phase, there are some constraints, right? And we split in the equation into two. One is for the tiptoe position, the other is for the heel position. So, and for the toe striking phase, again, there are a number of constraints. And so for the toe, there's theta dot toe is the velocity of the angle, toe angle, right? And all right, so I need to skip this. So about the swing phase, the trajectory of the tip toe in the swing phase is generated by using a fifth order polynomial, which is sufficient to make the trajectory smooth. So this is the trajectory for Z. And this is the X displacement in the forward direction. So for both heel lifting and toe striking phase, the leads of two legs are all stretched. And for the swing phase, only the lead from the standing leg is stretched. So the constraint for the lead for the three walking phases, and theta leads ST is equal to 0, and finally SW is equal to 0 only for these durations, right? And so you can see for the standing legs, this angle is equal to 0 at all times. As for the swing leg, this angle is 0 only for during heel lifting and striking. So here, these are the trajectories for the 6 joints, different joints, and different colors, so different phases. So you have a hip for the standing leg, and hip joint for the swing leg, right? So the ZMP calculation is based on this formula, right? So make use of the position and the acceleration of the each part, each body part at the center of mass, and also the angular velocity and acceleration of each part. They're altogether 7 body parts. So, and H is the angular momentum of the rubber body, and II represents the inertial tensor of each part with respect to the work frame in the same mechanics mode, and MI is the mass for each body part. So, right? So you can calculate, you can find the ZMP for a rubber body. And GZ is the gravitational acceleration. So now in our work, we try to adjust the position of 4 joints, all right, using this feedback mechanism. Right? This is the design ZMP. And this is the design ZMP found from the simulation. And then based on the difference, on the error in the ZMP, right, we can work out the change in the joint positions, the position of the 4 other joints. Right? So these 2 blocks are very similar, but we use different K value. They're scaling factor, K1 and K2. So I'll show you the derivation. And actually, the velocity of the angle of the 4 joints can be approximated by this expression, this, right? And it depends on the scaling factor times the change in ZMP. So for small sampling time, delta T used in the simulation, the approximate equation are used. So this change in the 4 joint positions can be expressed as a scaling factor matrix multiplied by the change in ZMP, right, multiplied by delta T. So this is the overall calculation. Right? First, we have the foot trajectory. We define step length and the heel lifting angle, toe striking angle, and there you have a generator, generate the XZ foot path, and then we use inverse kinematics to find the 6 joint positions, and then based then we have of course we have some initial value for the 4 other joints, right? So then we use this is a servo, and the output of the 10 joints angles assumed to be equal to this 10 angles, command angles, because we use the perfect matching servo system. Now, we then use the 4 kinematics to calculate the posture of the bipedal robots. And here you can see the ground contact model. It give you the friction force and the normal force. So then it will calculate all the linear and angular motion, right, of the robot, right, body parts. And then we can calculate ZMP, right? And this is the ZMP feedback mechanism. So we use this mechanism to adjust the position of the 4 other joints. So, and this is the simulation results. And then you can see this is the isometric view, the side view, and the front view. And we have 7 stages. 1 to 2 is heel lifting, and 2 to 6 is swing phase, and 6 to 7 is the toe striking phase. So we also estimate, do some estimation on the force on the sole, and at different stages. And the red color means high force, and the blue color means low force, right? So it shows the usual force experienced by the foot, right? Foot sole. So, and from A to B, you can see the force is evenly distributed along the foot width, right? Direction, because tilting is not severe in this period. There's no tilting. Pressure center move forward along the foot length direction as the body start to swing forward. So you can see you get a smaller force at the back. Swing is high force, sorry. And then you can see that, and then from B to C, the pressure center moved to the middle part. You can see some variation here along the foot length direction. And also you move to the inside edge of the foot. So it has a high risk to fall. And then when there is some tilting, you can see there's tilting effect here, right? And the normal force is evenly distributed, right? And so lastly, from D to E, right? You can see the pressure center move to the inside edge of the foot again as the body tilts back. So pressure for the front part is larger than the heel because the center of the mass has already moved forward. So this is the trajectory of the COM and the ZMP. First, the COM. Projection of COM for one walking cycle, you can see. And this set of diagram is for the tilting angle equal to 13 degrees. And you can see the plot of COM versus time. The two bounds this is the right bound and this is the left bound. And it shows that most of the time the trajectory fall inside the bound. And then for the variation of y against time, and you can see some part of it, all right, and only a very small part of it for outside the bound, right? So this is for COM. And now for ZMP, you can see the ZMP trajectory against time in one walking cycle, and the tilting angle, the maximum tilting angle is equal to 13 degrees. Right? And you can see that the trajectory of the ZMP for different phases. Right? This is for the x direction, x direction. Right? And this is for y direction. And you can see that there are for some period, short period, here, the ZMP fall outside the support polygon. So the value we use for the K and K1 and K2. Now here we just consider K2 because it's walking forward, right? And the only the side, the side. The ZMP Y matters, right? So this K2 bar is the nominal value, right? And different K2 will give you different beta max. And the value of K2 can be adjusted by multiplying K2 bar by the adjustment coefficient. So this is the definition of beta. So we plot the beta max against the adjustment coefficients. You can see it's quite linear. And so we can use a smaller value of alpha, and we get smaller value of beta max. When we use a larger value of alpha, you get a largest value, 16.9. So, and we also define the percentage of swing phase time for ZMP inside the support polygon. Right? So T inside, right? So the larger the T inside value, the better, right? Because it means that the ZMP most of the time will fall inside the support polygon, right? It means stability, right? And so considering all cases, when ZMP is inside of the upper bound, so we can make this as large as possible. So this curve will touch the upper bound. So the maximum percentage is 86.69%, based on the time, right? And the alpha equal to 1.45, the beta max is 18.85. So this 18.85 is desirable as the percentage of swing phase time inside the support polygon is maximum. For beta max less than 18.85, the robot walking motion will be less stable when a smaller beta max is used. So it doesn't mean that you will fall down immediately when you have SMP outside the support polygon for a short time, right? You can still walk, right? But now another concern is that we like to have a smaller beta max because it look more like a human-like walking, right? So this is the curve showing the variation of percentage of swing phase time against the beta max. So, conclusion? With the 3D bipedal model and ground contact model established in swing mechanics, the bipedal robot can walk stably with a given walking pattern. The walking pattern is human-like, which includes heel lifting phase, swing phase, and toe striking phase. By using the distributed force sensor model in SMP criteria, the stability of proposed walking pattern is successfully analyzed. The relationship between the robot stability and maximum tilting angle during swing phase can be obtained. So I just like to show you the simulation. $50 seconds only. You can see the tilting, right? During swing phase, tilting will occur. It tries to balance itself. So this is the end of my presentation. Thank you very much. Thank you for your patience.
Limitations in terms of the maximum speed, walking speed?
That may have some effect on the dynamics, right? Because if you walk faster, then your inertial effect will be larger, and then your ZMP will change, right? So that may affect the stability. Is it okay?
Yeah, nice talk, actually. I enjoy it. Thank you very much for that. I'm just wondering if that has been implemented mechanically, No,
we start to do the experiment.
Simulation.
So I leave Hong Kong. The Mr. Xi Chu is going to test it, right? It's already built the two legs. And
so it is under building,
Yeah. We have finished the simulation part. Actually, I think he's currently doing this experimental part.
Great. Yeah. I'm just wondering, Doctor, if you have, this sort of mode. As you said, when you go faster, the stability might deteriorate. So that might bring you to actually sort of upper level control, where you jump from one mode to another mode, like the mode of turning, the mode of going forward, the mode of something like that.
Something like that, yeah. Something like that.
Yeah, we did it actually with autonomous helicopters, where we see actually when it goes forward, the dynamics changes. The dynamics of the system itself changes. So maybe you need. I'm just wondering if you have considered something like that, or I see that maybe the research still at the early stages, the simulation.
Yes, the early stage, right? Yes.
Okay,
yes.
But that was interesting.
Yes,
actually.
early stage.
Thank you very much.
Yeah, thank
Appreciate
you.
it.
We saw in the model, like, there's only the legs are being modeled, or do you also account for the upper part of the body of the robot?
Up to this point, we did not account upper part. Only consider two legs.
Just as a curiosity, is there going to be like an application, or is it just for working legs for a robot in general, or
in general, just a general study. General study.
Okay.
Just last question. From your findings, do you think we can reach, something close to human walk?
It is in fact is a difficult topic, and we
Yeah.
try to do as much as we can. So
Yeah.
so actually the project started not many years ago, only 3 years ago,
I
right?
see.
And so we hope we can do more in this area, right?
Great. Yeah, hopefully. To be frank, it's a typical fuzzy logic weather problem, like the inverted pendulum and those things, you know. So,
yeah.
you know, this human way of thinking that
Yeah.
you don't do any sort of calculations. Actually, it's the natural,
Yes.
you know, logic that
Yes,
that gives you
in-
the stability.
yes, you're right. Because in our last project, actually, we use the neural fuzzy to plan the path, right?
Yeah, that's
and we finished the earlier part, but of course, we finished that part already.
That's
and that's optimization and using neural and fuzzy
Good.
for the
Good luck.
for planning.
Yeah, I'd like to explore more. Maybe I'll send you an email to see, you know,
Thank you very much.
some results. Thank you.
Thank you very much. Okay. Thank you very much. Okay.